In this chapter, we're going to be taking a look at chemical quantities. What we're going to be taking a look at is how to figure out how much of a substance we have, and there are lots of different ways to do it. The biggest way, the most popular way we have to convert things is through the mole. It's the most significant discovery and innovation in chemistry. It brought us out of the old world of alchemistry and into the new world where we're actually scientifically proving how much of a substance. So the mole is just quite simply an amount of a substance. We can describe amount of a substance in several ways. One way is to describe it in terms of particles. If we have a mole of water, say, we would have 6.02 times 10 to the 23rd molecules. If we have a single element, a mole would be atoms. And if we had an ionic compound, we would call it formula units. But basically, if we're doing to those particles, we would use the number, Avogadro's number, of 6.02 times 10 to the 23rd. Keep in mind the Cliff Hoburns: chlorine, iodine, fluorine, hydrogen, oxygen, bromine, and nitrogen. Those are diatomics. They do not exist as atoms, but as molecules. And so in this chapter, you're going to be seeing how we use that factor label method to convert. Now, essentially, this is it. This is what we need to use for the mole conversions. The mole is the core of everything. This number is always 1 when we're going through and doing conversions. So I can go from the mole to figure out the number of particles. I would use the conversion of 6.02 times 10 to the 23rd. If I'm going to figure out the mass of something, I would use what's called the formula mass. You simply look on the periodic table, see how many of each element you have, how much they weigh, and put that according to the mole. Now, the mole can also be used to figure out the volume of a gas, and we must be at STP, which stands at standard temperature and pressure, which is 101.3 kilopascals of pressure, the same thing as 1 atmosphere, and 760 millimeters of mercury, and standard temperature would be 0 degrees Celsius, or 273 Kelvin. Okay, those conditions must be there, and it must be a gas. A lot of people use that for water conversions or whatever. For a liquid conversion of volume, this is only true of a gas. Okay, so standard temperature and pressure, 101.3 kilopascals. In this chapter, you will always be at STP for those conversions. You can't go from volume conversion into mass directly because we have to go through the mole. And that is the commonality between those three. In class, we just say, well, you just can't do it because there's sharks. You're on a mole island and you just can't do it. But the truth is, you have to go through the mole for everything. Now, you're going to see some examples of how to do that. And we'll just take a look at a couple quick examples here that we went through in class. If I'm looking at here we're looking for moles, and here we have atoms of an element. So magnesium is a single element. We can go directly to the atom for that, 1.25 times 10 to the 23rd, and make sure you label that of atoms. I need to get rid of the label of atoms of magnesium, and I go directly to the mole. I can do that in one step because magnesium is a single element. 1 mole is 6.02 times 10 to the 23rd atoms. Label of atoms of magnesium is going to cancel out. I'll be left with moles of magnesium. Okay, so you just, in this case, divide 1.25 times 10 to the 23rd by 6.02 times 10 to the 23rd, and you'll get your answer. Remember, significant figures, 3 significant figures in your answer. Now, if I turn it around and I say, okay, I've got 1.5 moles of zinc, and I want to know how many atoms. Again, I see atoms, I think, oh, is that going to be for an element? Yes, it is zinc, so it's just a single element, 1.5 moles of zinc, and I get rid of the label of moles of zinc and put it into atoms. I can do that directly in one step because it's a single element. 1 mole, 6.02 times 10 to the 23rd. So in this case, we're actually ending up multiplying. But don't worry about if you're supposed to multiply or divide, just follow your labels. You'll be okay. Now, if we take a look at another example, I want to know how many, and I'll have to erase some of this so we can read it a little bit better. Here I want to know how many atoms are in 2.12 moles of propane. Now, again, I see atom. I wonder, okay, is this a single element? No, it's not. It's a molecule. So my Avogadro's number will only apply, and we're going to C3H8. Avogadro's number only applies, in this case, to the molecule. I can go from moles, C3H8, to molecules, because that C3H8, Avogadro's number applies 1 mole, 6.02 times 10 to the 23rd. Okay, that's only going to apply in the case, if we're going to the atom, it's only going to apply to a single element. So now I need to figure out, okay, in one molecule of C3H8, how many atoms are there of C3H8? Well, I've got 3 carbons, and I've got 8 hydrogens, so that's going to equal 11 total atoms. Okay, so it's as simple as that. It ended up being a 2-step process. Take a look, moles will cancel, then I'm in molecules, that'll cancel, and I'm left with atoms of C3H8, and again, don't forget, 3 significant figures. Okay, now let's take a look at how to do this when figuring mass. Now, don't get too torn up about this whole gram atomic mass unit, formula mass, and all those things. When I'm doing mole conversions, basically all I'm doing is figuring out how much does this compound weigh. Okay, your book will differentiate between gram molecular mass versus gram formula mass. This just simply means that what is the formula mass of a molecule or an ionic compound, a formula unit. So don't worry too much about that. But basically this is saying, okay, we're going to add up the formula mass. This is, with the sulfur trioxide, 1 mole would weigh 80 grams of sulfur trioxide. 1 mole of ammonium carbonate will weigh 96 grams. Now be careful with something like ammonium carbonate. We have to add that up, and how we do that is, and I want you to document it just like I did in sulfur trioxide here. We have to make sure that we distribute this too. So I have 2 nitrogens. I have 8 hydrogens. Don't add them. You need to multiply. 2 times 4. We're distributing that 2 inside the parentheses, so 2 times 4 is 8. I have 1 carbon, and I have 3 oxygen. So I go, okay, nitrogen weighs 14, hydrogen weighs 1, carbon weighs 12, oxygen weighs 16. Okay, this is 28 if I multiply. 8 times 1 equals 8. 12 times 1 equals 12. And then 3 times 16, that's going to be 8. That's 48. I add it up. I'm going to get 96 total grams. This way, if you show all of this work here, and you end up accidentally adding wrong or whatever, I'm not so worried about that. You know how to do formula mass and so on. You just can't add right. Okay, let's look at how we do that. Okay, what a problem would look like. Okay, I have 9.45 moles of dinitrogen trioxide. I need to get rid of the label moles dinitrogen trioxide, and I need to get it into grams of dinitrogen trioxide. I can do that in one step because on mole island, here's the mole, here was my formula mass. Okay, so I can do that in one step. Over here was particles, and here was volume. Okay, so I can do that in one step. I just have to say, okay, 1 mole. Now I go, okay, 2 nitrogen. I've got 3 oxygen. This is 14, and this is 16. Okay, so that's 48. That's 28, and 16. That's going to be 76 grams. Okay, moles will cancel, and just multiply 9.45 times 76. Be careful, 3 significant figures in your final answer. Okay, so this is just kind of breaking down how we did those. Okay, now if I flip it around, whoops, I went too far. Okay, let's flip it around. I have 92.2 grams of iron 2 oxide. Oh, now we have to remember this means iron has a +3 charge, oxygen has a -2, so I'd write it as Fe2O3. Now I'm getting rid of the label grams of Fe2O3, and I need to get it into moles. Fe2O3. This number is always going to be 1. Okay, then I go, okay, 2 irons, 3 oxygens. Okay, just figure out what that is. And this is 16, and just add that up. That number will go right in here, and 3 significant figures. Now, volume. Okay, again, we're remembering that standard temperature and pressure is 0 degrees Celsius, 101.3. We're going to use our number of 22.4. So, real simple problem. It doesn't really matter what the gas is. Any gas is 22.4. So I have 0.60 moles of sulfur dioxide here. I want to get rid of the label moles sulfur dioxide, and I need to get it into volume. That volume will be in milliliters they're asking for. I can go to liters and then simply go liters sulfur dioxide into milliliters sulfur dioxide. Okay, so moles have canceled, liters have canceled. Now I'm in the label of milliliters. I'm at STP, so I can say 1 mole is 22.4 liters, and then I say 1 liter is 1,000 milliliters. Problem's done. I have 2 significant figures in my final answer. I'm just multiplying 0.6 by 22.4, and then multiply that by 1,000. Now, here's kind of an interesting question here. The density of the gas. Now density, if you remember, density equals mass over volume. And here I see a label of 1.964 grams over 1 liter. Okay, so that's a mass over volume. I want to know what the molar mass is. Well, the label of molar mass is going to be grams per mole. Okay, so if I look at what I have here as my label, I just need to get rid of the denominator label of liters and get it into moles. So 1.964 grams over 1 liter. I need to get rid of the label liters, grams per liter. I need to get rid of that label liter and get it to moles. That will give me a label of grams per mole. A lot of students really struggle with this type of problem, but it's actually really easy because I'm at STP, and it doesn't matter what the gas is. Any gas, 1 mole, is 22.4 liters. I just simply multiply. Look at what happens. I end up canceling out the label of liters. I end up with a label of grams per mole. Problem's done. I just go 1.96 times 22.4. Make sure you have 4 significant figures in your final answer. Okay, now we can actually combine some steps. Okay, so we want to know how many grams of nitrogen dioxide are in 43 liters at STP. Now, remember, you can't do this in one step. If it helps you to draw out mole island, okay, here's your particles, here's your mass, here's your volume. Okay, this is 22.4, here's 40 millimass, here's Avogadro's 6.02 times 10 to the 23rd, and this number is always 1. Okay, so I've got 43 liters of nitrogen dioxide. I need to know how many grams. So I'm up here, and I need to go here, and then over to here. So I need to get rid of the label of liters of nitrogen dioxide. I go to the mole, and then I can go from moles of nitrogen dioxide, and I can go into grams of nitrogen dioxide. So I just bounce between the islands, do a little island hopping. That's lots of fun, real tropical. We have 1 mole now. Nitrogen, grams of nitrogen dioxide. I have 1 nitrogen, 2 oxygens. This is 14. This is 16. That's 32. This is 14. Now I have 46 grams. Okay, so 43 times 1 times 46 divided by 22.4, and I have 43 is the number I'm supplied, so my final answer will be 2 significant figures. Problem's done because I've gone from liters to moles, moles to grams. Now, how many atoms are in 43 liters? Now, be careful. Again, here's mole island, and I'm going from that here. Now we want to go to particle island, and I'm going from volume, okay? So be careful. There's atoms, and I look, oh, this is not an element, so I'm going to have to do one more step, aren't I? 43 liters of nitrogen dioxide. I need to get rid of the label of liters of nitrogen dioxide, get it to moles of nitrogen dioxide. I can go now from moles to my particles island, but that label is molecules. MOLEC nitrogen dioxide. And then I say, okay, I need to get rid of molecules of nitrogen dioxide, and I need to get it to atoms of nitrogen dioxide. Okay, so 1 mole is 22.4. 1 mole is 6.02 times 10 to the 23rd. And then 1 molecule of nitrogen dioxide contains, okay, I've got 1 nitrogen, I've got 2 oxygen, so that's 3 total atoms. So be careful on that step. You can't go directly from moles to atoms. You have to go moles to molecules, then molecules to atoms. Okay, so you can convert any of these. You can go from atoms to mass just by doing those conversions and so on. I think you get the idea from that, and good luck with your conversions.